Okay, hello, this is Dr. James, and today I'm going to talk about the, what is this, S-A-A-2 little network analyzer. It's good from 10 kilohertz up to 3 gigahertz, and it gives you Smith charts, it gives you log magnitude, it can do all sorts of different modes. Portable, handheld, it's good for a lot of different projects, and I'll demonstrate its capabilities and its limitations. Less than $100 for this guy. Very cool, huh? Let's get going. Okay, looks like it finally arrived. Let's see what this, I don't know what the top is and the bottom is. Let's try this side. Okay. Let's just do this. Okay. Let's see what's inside this box. I think I know what it is. Okay, what is this? Simple vector network analyzer. Oh, look at that. Now, I remember when I was in grad school, these things, you could only get them from like Hewlett-Packard, and they were outrageously expensive and huge and clunky. And now, you can get this one for less than $800. Look at that. Oh, very cool, huh? Let's take a look here, see what we got. Let's see what's inside this bag here. Oh, there we go. Look at that. Oh, wow. It's open on the sides. Holy cow. So it's like 1.5 ports. You can do a through measurement and you can do a reflection measurement, but you can only do a reflection on one side. See that? Let's take a look at this. Okay. So there's our network analyzer. It's got the directions on the back and looks like a screen on the front. See, it's got an out and a return there, and just a return here. SMA connectors and some buttons here. Wow. Looks like a lithium battery and micro USB port there. And a little switch on the side here. Very cool, huh? So this one is supposed to go up to 3 gigahertz. Let's see what else is in here. Some kind of directions. Oh, that's confusing. Looks like some kind of memory map or something of all the different buttons you can press. No explanation as to what they are. Wow, what terrible directions. Oh my god. Okay. Micro USB cable to charge it up. Maybe these are standards for calibration. I'm not sure, they're not labeled. Some hardware in there. Some short SMA cables. Let's get those out here. Yeah, see? Some short SMA cables. Looks like some kind of pen. Maybe that's for writing on the surface of this guy. Hardware. Okay, so maybe we'll charge this thing up, and I assume it's got to be charged. The directions are absolutely awful. Gosh, I don't know what the heck these are. Usually with a network analyzer you have to calibrate it with a short, open, and through, and there's no labels on these things, so I have no idea. That doesn't look like a short, that looks like a cap. That one could be. It's got a pin on it. I'll have to look at these. And okay, here's our USB cable. So let's just plug that guy in, and then we'll try charging it. Okay. Actually, I have a micro USB cable over here, So I'll just use one of my ones I got plugged into my computer already. And let's see here. There is the port for the micro USB right there. Okay. And let's just plug her in here, I guess. Okay, when I do that, it looks like these lights come on. And maybe it's charging, who knows. I'll just let it sit for a while. And we will see what this thing does. Okay, so here's the description on the box. S-A-A-2, simple vector network analyzer. Frequency is supposed to be 50 kilohertz to 3 gigahertz. Okay. 5 volts USB input. And this is hardware version 2.2. Okay. And I think that will cover the frequency range that I'm interested in, because I wanted to test out the losses of my Tesla coils. And you could use this for antennas or microwave circuits or whatever. 3 gigahertz is pretty high frequency. That will cover a lot of S-band for microwave enthusiasts out there. Should be interesting. Okay, I let this thing charge for hours, and these lights that were blinking are now just kind of staying on constantly, so I'm going to guess that maybe it's charged up. Okay. That's interesting. I wonder what happens if I flip the power switch on. Oh, look at that. Smith chart. Oh, this is so awesome. Okay, anyway, I'll have to figure out what this sweep is, but Smith chart is something that tells you what the impedance of your source is. These are open circuit, so it's going to travel around the outside of the Smith chart. It would be just a reactive load. If it's matched load, matched to typically these are 50 ohms transmission lines, then it will be in the center. And as the frequency changes, the wavelength changes. So for a given path distance, it will start traveling around the Smith chart, because you represent the electromagnetic wave as a spinner, and so it's spinning around in circles, basically. The phase is spinning, and a changing phase changes the reactance, or the impedance of your load. Let's see. So this is probably just, I'm going to have to fiddle with this some to see what we're measuring here. Typically, okay, I guess it was upside down. Typically, I like to view things not in the Smith chart mode. This will tell you what the impedance is. Actually, probably I'm going to do some measurements on my Tesla coils with the Smith chart, because I want to see what the load, what the internal resistance of those guys are. But typically, I'll just do a dB plot. dB versus frequency, because you can't really see the frequency on the Smith chart. You just see how the impedance varies. Okay, I'm gonna have to fiddle with this and see how we can change this into a different mode. Should be interesting. Pretty amazing, huh? Super cheap network analyzer. Okay, so I just wanted to take a second to talk about the calibration kit. Now, when you're using a network analyzer, you need to calibrate the network analyzer, and you can calibrate it to the end of the cable. But let's say, okay, let me get a cable here. So you could calibrate it right to the port of the machine, but the network analyzer actually tells you phase. So as a signal propagates down the cable, the phase will change, and of course the impedance will change as the phase changes. It goes around the Smith chart, and capacitive, reactive loads can become inductive and so on as you go around the Smith chart. So you can calibrate either right up next to the instrument. Let's get the instrument out. Like so. You can calibrate right at this port here. Or if you want to take out the cables, make it seem like the cables aren't even there, calibration is just a mathematical operation that subtracts out any losses you might have in the cable or the phase changes. You can calibrate to this point. And so that's why it's important to do a calibration. When you do the calibration, it takes out all of this loss, all these phase changes, and you can calibrate to any point that you want. And in order to do that, let me put this equipment back away. You need, there's a couple different ways to calibrate network analyzers, but at these low frequencies, the main way that I know is using a short, an open, a load, and if you have a 2-port, a through as well. And so it looks like here, these are unlabeled, but these are our calibration standards here, I'm sure. You can tell by looking at it. So, if you look at this guy here, it has no pin on it, right? It's just got an open area. And so this has got to be the open circuit because there's nothing connecting to the pin, to the center. A short would be something that connects the center pin to the outside with a just with a conductor. You can see that this is a metal conductor. It's a pin in the middle, and it's absolutely shorted to the outside. So this would be our short. And by definite product of elimination, this one would have to be the 50 ohm load. I'm going to guess it's 50 ohms. We could actually check that. And of course, if you're doing a calibration with 2 ports, you have to do a through as well. You have to send the signal in one side and out the other side, and the cow would know what the phase shift is traveling through this short distance here. Okay. Just for... Oh gosh, where did that go? Just for amusement, let's get our volt ohm meter out. Okay, we got our ohm meter right here, and let's just measure. Okay, we'll get our volt ohm meter out. Okay, and we'll just measure the impedance of the termination that I suspect is probably the 50 ohm load, which is this one right here. So we have it on ohms. I'm going to touch one pin to the outside and one to the middle. If we look at the voltmeter, it says 50 ohms down there. Can you see that? Okay, and see, it's about 50 ohms there. Let's get the pin back on it. Okay, there we go. I got it on the pins, and it looks like it is about... Okay, and there we go. It looks like it is about 51 ohms. Close enough. Okay. Okay, so anyway, these are the 4 standards that you use to calibrate the network analyzer, and you want to do that because you'll get a better measurement. Okay, and you'll be able to take out losses of the cables or whatever. If you want to do a more accurate measurement, it should be interesting to see how this network analyzer performs. Okay, so the next thing we're going to do is try to calibrate it with these. And remember, the first thing you want to do is choose the frequency range before you do a calibration. Okay, so I'll just quickly talk about the theory of S parameters, which is what the network analyzer measures. There's different ways to measure what do you call it? Networks or circuits, and S parameters is one way. Typically, with low frequency stuff, you'd use like a voltmeter and an amp meter. Right, here's a voltmeter or an oscilloscope measuring volts and amps. And that only works if you don't have very high frequencies, where you have a wave when it becomes a very high frequency traveling down a transmission line, and that wave can change voltage as it travels down your leads of your voltmeter. Right, travels down the leads of the voltmeter, then it would have a different voltage as it gets up there. And of course, I shouldn't use voltmeter, I would say that's just for DC, but oscope, if it's not if it's very high frequency, your oscope can't deal with it because it behaves like a wave. And so when you're using waveguides, rectangular waveguides, or RF, very high gigahertz frequencies, the only way to really deal with that is, so a waveguide doesn't have two ports, it's just got a single cylinder around it. You can only deal with waves, and the network analyzer S parameters are designed to deal with waves. So you have a wave that comes out, and it will go into your circuit, and part of it will get reflected and return back to the source, and part of it will go through if you're using a through measurement with two ports, and you can measure how much power is reflected, how much power goes through, and of course if you have resistance in your circuit, you'll get losses. And the network analyzer, using S parameters, can tell you these three parameters versus frequency. So it generates a frequency, and then it sees how the circuit responds to it. It sends out a wave into it, and then looks for a reflected wave and a wave that goes through. And anyway, this is the theory. And the inbound wave is defined as S11 is defined as the return wave divided by the outbound wave, and S21 is defined by the through wave divided by the outbound wave. Okay, and so that's the theory of scattering parameters. Let's move on and take some measurements. Okay, so let's start off with doing a calibration on this guy. So the first thing we're going to do, okay, so this has got a touch screen, and it starts out with a certain span in the frequency, and what we're going to do is we're going to go to stimulus. We're going to click on the screen, and that brings up a menu here, and it says stimulus right here. And we're going to say start. I'm just going to calibrate it over the whole range. This is probably not super useful because it's going to have a lot of spaces between the points, but just to see how this instrument behaves in general over the full range. 50 kilohertz, 50K is the lowest frequency that we're going to get. Okay, and we're going to put a stop frequency. I prefer start and stop. Okay, because well, it depends on what you're doing, but in this case I'll just say 3 gigahertz. Okay, and so it comes up with a Smith chart representation and a log chart. And if you look at the Smith chart, for a good cal, it should, since it's an open circuit, should be around the edge of the circle of the Smith chart, and it's not super great over the full range. So typically we will put wires on here, like so, cables, let's call it cables, through the in and the out. If you're going to do a through, you can either do, it depends on whether you want to do a through measurement or a reflection measurement. This port over here can do a reflection, and there's a second port that's only a receiver. It can't do a reflection. It can only do through. So if you had a device where you're sending a wave out here and it comes in over here, then you would use the through option. Otherwise, what you would do is you would just look at a reflection from an antenna. So typically you'll have two cables hooked up here. And let's take these protector things off. This is just to protect the SMA connectors so they don't get junk inside of them. Okay. And again, these are SMA connectors. See, SMA. And let me just put these cables on here. So we will screw these guys in. Then we'll just do the cal up where we can see it. Look at that. So now it's going around the Smith chart a lot more because it's going the full length. Let's take a look here. It's going the full length of this cable before it reflects. So it's going zoom, zoom, zoom around the Smith chart. Okay, and like I think I said before, the calibration is capable of taking out that phase. You can calibrate out to the end of the cable. And typically these cables have a certain bend radius, so you do not want to bend them more than what they want to be bent. I think I can probably bend them around to do the cal here. So we have different standards, and of course the SMA is males, and all of our standards are also males. So I'm going to probably use the through adapter here, the through adapter to adapt. It's a female, so we can calibrate our standards. It's going to be a little bit off, but what you're going to do, because we don't have a standard for the female part, so I'm going to 3 gigahertz. The wavelength is not going to shift that much. Now typically you want to spin the nut and not the connector, because especially if you have high precision connectors, it will mess up the pin on the inside. Okay, let's do a cal. Oops, let's see, we're going to want to go back. So we're going to go to the cal menu. Okay, hit cal, and we're going to, the top selection is calibrate, and I'm going to put the different standards on here. I think I will start with the load. So here's the load. Remember we talked about how the load has a Teflon in the center and it has 50 ohms across it. Okay, so let's grab this guy here and we'll screw it onto the end. Oops, you know what? I put that on the wrong one. I put that one on the through only. We're never going to have a load on the through. All of our calibrations will be on the other cable except for the through. So it will be on this port right here, and so this cable, see, it comes around like that. Let me put our adapter on here. Okay. And we will put our load, this is our 50 ohm load here, onto the end of this cable. And if you watch the Smith chart when we do that, it should go into the center more because it's going to be matched. See that? It's not perfect, but that green circle thing went from being all the way around out the outside to being matched, and our log charts also came down, our reflection. Okay, so we're going to say this is our load. Okay, so we'll hit load, and it's going to sweep through and take a bunch of measurements. Okay, now the load is highlighted since we finished that one. So we'll take off the load. Okay. And we will put on this one that's completely metal is going to be our short. Okay. I'll put that guy on there. Okay. That's not going to change it too much because a short and an open are very similar. They're just 180 degrees out of phase, but they're both going to stay around the outside of the Smith chart. So we will call this one short, and we'll hit the short button, and it will take measurements on that. Of course, reflection is going to be high, so our log scale is going to be high up there, the yellow trace. and the phase is going down the line. Okay, so it says our short is done, so we'll remove the short. You will see a jump in the phase, but it'll still stay around the outside of the Smith chart, so it's not going to be as apparent. And let's do our last standard, which has no pin in the middle, so this is going to be our open. Okay. And we'll hit open up here, and it's going to take the measurements. And when it's done, let's see, did I hit it? Maybe I didn't hit it. Okay. We'll hit open. It's hard to tell if it received that or not, because it should turn black once it's been measured. Open. Okay, so open has been finished now. Okay. We'll take the open off, and we will do one last measurement of the through. So we're going to hook these two cables together. So it's going to, see, now we're getting the blue traces coming up. That's the S21, or through measurement. And the green one, okay, so we just hook this cable, the output, to the input, so we can get a through measurement. As you can see, the through S21 trace, which is this top one, log magnitude, goes very high, which is showing that we're having very low losses through the whole system. The green trace, the Smith chart, went into the center, which means it's pretty good matched. And the reflection traces came down, and then the phase is, of course, it's going through the cable. The purple trace is the phase. Yellow one is log magnitude reflection, which is low, several dB, 10, 20, 30. So it's very, very good through, or very good low loss reflections, not very much reflection. And the blue trace is the log magnitude of the throughput of this guy, which is almost 0 dB, or close to full wave transmitted through. We got our cable hooked up, and we're going to hit the through measurement. Okay, and it's going to take measurements at all the different frequencies, and it says it's highlighted at black. So now we're going to hit done, and I'm going to save this as 0. A lot of times it's a pain to save do all those calibrations. So, I mean, our cal is okay. It's not super great, because the green one should be completely in the center, since this is our cal. The yellow one should be very low. Of course, at the high end, it's only about maybe 18 dB down, it looks like. I'm assuming that's 10 dB per division. Yeah, it says so up there. The blue one looks pretty flat, and it should be close to 0. 0 dB means there's no losses going through. Remember, we've calibrated this and said this is the no loss situation, so we're taking all these cable losses out and in the calibration. And of course the phase is going to vary because it's going down a transmission line, but ideally the yellow one should be lower if it was a good cal, and the green one should be right in the center of the Smith chart, which means it's perfectly matched. So I would say that this network analyzer is probably accurate to about 15 dB or so at the high end. It looks more accurate down here. You know, this yellow trace, if it was a HP or something like that, it would be like down 80 dB across the floor. So this is, you know, it's not super high quality, but it's good enough to do measurements. I mean, 15 dB is what? 10 dB is a factor of 10. So 15 dB is a factor of 13 dB would be 20. So probably about a factor of 40. And signal, or I don't even know what you'd classify that as. Probably signal to noise. So it's not super great, but it's okay. It's good enough to do the measurements I want to do. Anyway, there's our cal. It's finished. Smith chart and log magnitude of through, reflected, and we have the phase in the Smith chart there. So there's our finished calibration. Pretty cool, huh? We're going to do some real measurements on circuits now. Okay. Should be interesting. Okay, so here's our next project for our network analyzer, and this is something that's really designed to do. We have this mystery antenna here. Look at this. Oh, very cool, huh? I think it's a log periodic antenna. Broadband. Let's take a look at this. So, let me talk a little bit about antenna theory, since I'm a RF antenna engineer as well. Typically antennas like this are matched at the frequencies that they operate at, because you want to transmit all the power that you're putting into the antenna into the what do you want to call it? The into space, free space, we'll call it that. And so you don't want reflected waves. You want the power to go into the antenna and be transmitted out, so it goes to the other antenna. So you want it to be as efficient as possible. And so typically they will have a good match or low reflection at the frequencies that they're designed to operate at. And a lot of times they will not have good match outside the band. So we might be able to tell. I'm not sure, you know, this thing doesn't have really any labeling on it. I'm not sure what band it operates in, but if we put it on the network analyzer and see, judging by the size of these radiators, I'm going to say, I could probably do some calculations, but it's in the gigahertz range. It's like maybe 1, 2, maybe 3 gigahertz. If it's higher than that, I don't think it's going to be higher than that, because these radiators are too big down here. We won't be able to measure it with the network analyzer, but we should see S11. We're just going to do a single port measurement. S11 should go very low over the range of where this antenna is operating. And so let's hook up our network analyzer, and I'm going to just do a broad sweep over the whole frequency band. Actually, you know, maybe I'll narrow it down. I'm going to guess it's probably above a gigahertz. So I'm going to limit the start and stop frequency, or the start frequency, to higher than 50 kilohertz. This is definitely not a 50 kilohertz antenna. It's probably around 1 gigahertz or 2 gigahertz or so. And we will take some measurements using just the one port. We'll send a wave into this antenna. Okay, so we'll send a wave going into the antenna, and then we'll see what's reflected back. Okay, and a little bit later we'll do some through measurements on some interesting things. Okay, but let's, for right now, we'll just do a S11 measurement of this guy, and we'll see if we can determine what its bandwidth and its frequency range of operation is. Should be interesting. Okay, so let's set up the frequency range first. Okay, and of course we tap over here to get our what do we call it, our little selection buttons here, and it's going to come up with this main menu, and it should say display, marker, stimulus, whatever. We're going to click on stimulus, because that's how we change the start and stop frequency, or the span, the number of points, that type of thing. And I'm going to change the start frequency to, let's say, 100 megahertz. Okay, because I'm sure that the start frequency is at least that. It's going to be much higher. It's going to be in the gigahertz range, but I just want to make sure I'm covering the whole range. And the stop frequency will go up to the max, which is 3 gigahertz. Okay. Okay, there we go. And I'm going to, since I have a female, I was thinking about calibrating just up to this point, but I guess my adapter is female, so I'm going to need a male, so I put a cable in there, because this will give me a male. And I'm going to calibrate just up to this point. Actually, maybe I'll do a through anyway, because it doesn't seem to give me an option for just a one port. So I might just hook this up to this point to do the through. So we'll do the calibration. Let's see. We gotta go back. We'll hit the back button here. Okay, so it's display, marker, stimulus, calibration. Okay, click on calibration. And top menu button is calibrate. So we can do the open, the short, the load, and the through. So let me get my standards ready, and we will try to do the cal on this. Okay. Okay, so again, all these calibration standards are male type, and here's our open. Let's just start with the open. So in order to connect these to our cable, which is a male, I'm going to have to put a female to female adapter onto here. So let me go ahead and do that. Okay, so I just screwed that guy on. So let's start with the open, and I'm going to put the open on our adapter here, and so we'll screw that guy on like so, and I may have to put the camera down to tighten that up, but actually it probably doesn't make a difference because open is just nothing anyway. Okay, so we'll hit open, and now see it's highlighted black that we've taken that measurement, and we'll take this standard off, and we will put the next standard on. Now, typically when I was doing calibrations with like HP network analyzers, they would have a torque wrench, because you want to torque these up to a certain torque spec. So anyway, we don't have that on this cheapo one. This is going to be our short. See how it's metal on the inside? It's got a pin and it's shorted there. So we'll do the short next. You don't have to do these in any particular order, but I will because I just feel like it. Get it started. Okay, there we go. So we got the short on there, and I think that's fairly tight. Okay, so we got the short on there, and we'll hit short calibration, and it's going to take a sweep, and then see it filled in black for short. Okay, so we'll take the short off, and okay, so there again is our short. It's got the metal on the inside. So our load is going to have the Teflon on the inside because it's got a 50 ohm resistor in there. And we will put that one on the end of our cable here. I can do that with one hand. Without this thing moving around on me. Okay. Okay, again, see when we put the load on it, remember our Smith chart goes into the center, because that means it's matched. If it's going around the outside, it's reactive or open circuit or a short circuit. The green one is our Smith chart, so perfect calibration should just be a dot in the center. But if you have errors, it will just kind of meander around. The yellow trace is our reflection or S11 trace, and of course that goes down because we're matched, so that's telling us that the wave is coming out of the device and it's coming to the load and it's getting absorbed there. Not very much is getting reflected. This is a measure of how much is reflected, so you really want that to be low. And the purple trace is the phase, and of course we don't see the other trace, the blue one, because that's the through, and there's nothing going through because there's no power going back into this guy. Okay. So let's go ahead and we'll calibrate for the load. Okay. See if I can push that button. Okay, there we go. And I guess I'll go ahead and do the through, because I don't know what algorithm this network analyzer uses, but it might want to have all parameters in there for it to do the calculation of the S parameter calibration. So we'll unhook that guy, and I'm going to unhook this adapter here. I'm going to have to put the camera down for that for a second, I think. Okay, there we go. So I got it loosened up. So this is just our adapter that came with our network analyzer. And there we go, we got that guy off. And I'm going to just hook this output back into the through input here. So if I can get it lined up, this thing wants the torque on me. Come on. Get it lined up. Okay, there we go. Okay, so there. So now we're feeding the signal out here through our cable and then back into the through. And again, the S parameter, the Smith chart, is kind of toward the center. It should be perfectly in the center if it was a perfect match. And our S11 is low. It has some reflections. You can see that in the ripple. And oh, see, now we're getting a through measurement. See, the blue one is through, so we're getting power through the device. Remember, it was very low, and now it's very high. Okay, so let's click our through, and it will take the measurement on this guy, and then it highlights the through. Okay, so our calibration should be done. So we'll click done. Actually, look at, it's not too bad. See, the Smith chart is pretty close to the center, which is what we'd expect for a good cal. Let's see, how do we get out of this? I want to get out of this. Okay, again, like I said, the S11 is the reflection. So in a good cal on an HP network analyzer, this reflection would be very low. It would be 80 dB down, 70 dB down, something like that. It's kind of like the noise floor measurement of the instrument. This reflection right here at the high end, the gigahertz, it's probably about 18 dB, so it's not super great. I mean, 18 dB is good enough to, do home stuff, I guess. It's, the 20 dB is a factor of 100, so 1 part out of 100 would be the error. So if you're not doing things more precise than that, then you're probably good to go at the higher frequencies. That's probably close enough. See, the blue one is the through. The through looks very good. It looks very flat at the top, so it's saying we're getting pretty much all of our power through. And then, of course, it recalibrates the phase up to this point here at the end of the cable. And so the phase variation is pretty constant as well. You can see before it was like flipping from, going all the way through 360 and then coming back on the top. That's what the sawtooth is telling you. And so the phase is much more constant now. Okay. So I think we might have a good calibration. And again, I put it from 100 megahertz up to 3 gigahertz or 3000 megahertz. Let's hook up our antenna and see what kind of measurements we get from that. Okay, so I'll unhook this guy here and hook the antenna up to this, and we'll just take a S11 measurement or reflection measurement. Okay. Let's see, our through trace dropped as soon as we took the power off. Very interesting, huh? Very cool. Okay, so now we have our antenna, our mystery antenna here, hooked up to our network analyzer. Okay, and let's take a look here. Let's just, oh, look at that. So cool, huh? Isn't that cool? Look at that. That is amazing. Take a look at this log periodic. Okay, so what we got here is it looks like probably around 1 gigahertz. Our S11 is dropping down some, and it looks very broadband over here from 1 until up about 3. So I'm going to guess this is the bandwidth of the antenna here. Of course, it's not a super great match. Of course, you can't really tell because, like I said, the noise flare of this network analyzer is about 18 dB, and you can see it's 18 dB there. And of course, we have the phase varying here. That's due to the waves propagating down this long transmission line. And oh, I guess we're getting some. We shouldn't be getting any through measurements because. Anyway, so I'm going to guess this is our bandwidth from probably, what would that be, about 1.5 gigahertz up to 3 gigahertz or more. Very interesting, huh? Okay, so here is our network analyzer and our mystery antenna. Okay, very cool, huh? Okay. Okay, so here I have a LC circuit that I'm working on with a tunable inductor that I did a separate video on. And I'm going to measure the resonant frequency of this. So this is, see this, you can use this for regular circuits as well, because it goes down to a fairly low frequency. And I know the resonance is going to be between, let's say, hopefully, we'll go down to 100 kilohertz. And I may narrow the range later, but you got to do the selection of the frequency before you do the calibration. And it should be below, hopefully, 500 kilohertz. Okay, it should be in that range. Okay, if I did my calculations correctly. Okay, so we got some capacitors, high voltage capacitors, and it's going to be a pulse power unit. And a tunable inductor where I have a coil here, and I'm sliding, I wanted this inductor to be linear up to high power, so I'm sliding a copper slug in here. And I can slide this in and out just manually. I put some tape on it, so it's kind of stuck in there now. But see, I can slide it out. It's a plunger. I can slide it in, and that should change our inductance. Okay. And I'm not going to go through the calibration process on the video here, but I'm going to recalibrate it up to these frequencies. Okay. 100 kilohertz to 500 kilohertz. And we'll see how this... I'm going to have to put some adapters on here because I need to adapt from SMA to... I'm just going to hook clip leads. So I have a... let's see. Oh, gosh. It's hooked up to something else right now. I have a BNC cable here. So this is BNC connector. These are SMA connectors. And the BNC goes to clip leads. So I'm just going to hook some clip leads up to this guy. And I'm going to get an adapter and hook it up to this. And so we can adapt BNC to SMA, and then we can take, again, just S11 measurements with this guy. Okay, so let me get this calibrated up, and we will take some measurements here. Should be interesting. Okay, so I just finished the calibration, and I still have the load on there, and it looks like the calibration at these frequencies is pretty good. I mean, we're down... with the S11, that's like, what, 40 dB down. And if you look at the Smith chart, it's just a point in the center, which is what we'd expect for a good match. Very flat phase. Of course, we're looking over a very small range also. I'm only going 100 to 500 kilohertz. So let's hook this up to our device now and see how it behaves. Should be interesting, huh? There. Pretty cool, huh? Okay, so here's our adapter. This is SMA on that side and BNC. And so I'm going to hook this up to our cable connected to our network analyzer. Okay, can't do this with one hand. Okay, so we got it hooked up there. And again, I have my the clip leads here with the B and C connector on the other side, so I'll hook this guy up here. And see if I can do this with one hand. Oh gosh. Come on. There we go. Okay, so we get it hooked up, and you gotta push it on and twist it. Okay. Okay, and then I'll take the other end of this guy and I'll hook it up to our circuit. Probably just hook it up here, see how this behaves. Hook it up, shunt it across the inductor, our variable inductor. Okay. Oh, look at that. Okay. Oh, see the dip? That's where our resonant frequency is. Now let me try to slide this plunger in and out and see if we can tune that resonant frequency. It should tune. Okay. Let's go back. Okay. Let's see if I can figure out how to, see that? See it shifting? I'm pushing the plunger into the middle of this coil here. And that resonant frequency is shifting. Of course, it's becoming less deep, which means the Q is less now. Oh, you can see a big phase shift also. See that? The phase shift position is changing. Let me push the plunger back out. Okay. Come on. Get something to push this back out. Okay, so I push the plunger back out, and we'll try that again. Okay, so I got our copper plunger here. Okay, so it looks like I'm sliding the plunger in. See that? I'm pushing it in. As I push it in, our frequency is shifting. Of course, I have to wait for it to update the trace. Okay, there. Look at that. Okay, so it looks like we have some cursors, so I'm going to have to figure out how to move the cursors around. And then we'll see if we can measure what the frequency shift is when we tune the plunger here. Of course, I'm not really liking the fact that the Q is dropping. See, if it's deeper and sharper, that means it's got a higher Q. And so I guess you'd expect that if you are putting something in the middle of the coil to force the flux out of it, probably the Q would go down. Okay. Oh, okay. And let's take a look at the Smith chart. See, the Smith chart is having a circle around here, which is telling you that this is a... Oh, let me see. I believe this is mostly real part, mostly lossy load, and you can calculate what the impedance of that is from the Smith chart. But it has a little bit of a reactance part that's shifting around during the frequency. Remember, the Smith chart around this way, I forget, it's like capacitance this way and inductance that way, and then right in the center is matched so that it's 50 ohms real only. And so if you're along this line here, it should be real. And if you go this way or that way, it becomes reactive, inductive, or capacitive. So this is kind of a real load. We're getting real losses, and it's not matched to 50 ohms. I have to look back to see whether this is a higher impedance or a lower impedance, because I forget. I think this is a higher impedance. I think low impedance is down here. It's been a while since I've been looking at Smith charts. Okay, so let me see if I can figure out how to move this cursor, and we'll see what kind of frequency shift we get with our tunable inductor here. Okay, should be interesting. Okay, so I was fiddling with this a little bit, and I figured out how to change the where the cursor is. See, there's 3 buttons down here. This one shifts it to the left, this one shifts it to the right, and I think the middle one selects which trace that you're on. Let me just push the middle one. So it sees right now the yellow one's highlighted up here at the top. Okay, oh, okay. I guess it brings up a menu, so I'm not sure exactly. Okay, I guess maybe it shifts all of them together. So let me, yeah, see, it shifts all of them. So I'm hitting the left one to move this down to the minimum, and it looks like, does it have the frequency? I guess it just tells you the dB, it doesn't tell you the frequency. Or does it? Does it tell you what frequency it's at? Okay. Yeah, okay, the frequency is over here, and the dB is next to the trace up here, so it's, oh, come on. So it looks like that's about 9.3 dB, and it's at 244 kilohertz. Okay, so there is our resonant frequency. And so let's push our plunger in a little bit and see if we can shift the frequency. Okay, push this guy in a little bit, and we will take a look, see the frequency shifting. Okay, and we were able to shift it. I pushed the plunger pretty much all the way into the middle of the coil. So now our resonance isn't as good, but let's go up here, see how much we shifted it. Okay, so I'm pushing the far right button now. See that? Far right button down here. And that moves the cursor that way. And so it looks like our Q is not as good. It's only going down to about 5 dB. And our resonant frequency is 268 kilohertz. So, looks like we, I guess I must have miscalculated because I wanted the resonant frequency to be up around 370 kilohertz. So what I might have to do is I might rewind this inductor, because I want it to be closer to our resonant frequency, and hopefully operating at a higher Q point, and so with less of this plunger slid in there, and I'll just use this plunger as a trim, hopefully, to try to get this a little bit closer to the right frequency. So let me fiddle with that. Of course, you can see there's a big shift in phase at the resonant frequency, which I guess you'd expect that. Well, actually, you know what's happening here? It's not really a big shift. It's going from, it wraps around at 360. There's a variation in phase, but it's more of a like, see, this is Lorentzian function up here, the real part, and then the imaginary part, which would be the index refraction for optics, or the reactive part in circuitry. That has a part that is flat, and then it goes up, and then it comes down, and then back. It's like the derivative of the Lorentzian. So, but this is the zero phase, so it's going from zero phase to 360. So that's why it has this phase jump. So it's doing this variation, and then it comes back over here. Okay, so that's all that is it's skipping from 0 to 360, and it, that's the only way that they can't represent the phase wrapping around on a network analyzer. They have to cut it off some point, so it's got to go from 0 to 360, and so it has a jump someplace in the plot. Okay, that's not a real jump in the phase, that's just the way they have to represent it in a real screen. Okay, so very interesting. So we've learned something new, and here we have our circuit. Oh, so cool, isn't it? So cool. Very cool, huh? So our network analyzer is Now, I showed kind of before how you could do this, you know, if you have a signal generator and an oscope that goes up to this frequency. Of course, my oscope doesn't go up to 3 gigahertz, so this network analyzer can measure resonances much higher than I could do with this other method. So this is actually a handy tool that extends my capabilities. Very interesting. Let's see, we might try to do some through stuff in a little bit. That'd be cool. Anyway. Okay, so here's another way you can vary the inductance. Of course, I want to go up to higher inductance, or I mean lower inductance, because I want to go to higher frequency. So see the frequency here, let me see, I have the coils all tightly packed down here, and the frequency is about 260 some kilohertz. So what happens if I let the coils slide out like this? Can you see that? As I wrap it less tightly, the Q is going down, but our inductance is going down too, so we're going up to a higher frequency now. So if I stretch out the coils, it goes up to a higher frequency, and if I recompress the coils, the frequency slides back down. Okay, so here's another way of tuning an inductor, and I might use this. This might be a simple way of doing it as well. See? Of course, if you have the coils tightly packed, you can see that you have a higher Q. There's a deeper dip there. So I might fiddle around with this until I get an inductor that I'm happy with. And of course, I'm adding extra inductance with all these clip leads, so I might want to shorten up these clip leads and tie it directly in the way it's going to be tied in to see if that makes a difference, because this extra inductance could be bogging it down as well. I want to have a compact unit. Okay, should be interesting. So I took out the clip leads and I just hooked them in directly the way they would be hooked in if I'm going to use this as a pulse power device. And actually just doing that brings us up to the frequency that we want pretty much. What are we at? Okay, so then I can actually tune this by squeezing these coils in or out, and then I could probably hold them into place. Okay, so this might be a good way to... Oh, it's pretty high Q too. Okay. I need to hold them constant in place though, or else... Okay, let's see what our frequency is if we squeeze it down. Oh, look at that. Oh, a very high Q. I squeeze it down like that. So I might want to get rid of some windings because it's too high of a frequency still, or too low of a frequency. We need less inductance. And if we need to tune it, we can always maybe spread out the coils a little bit so we can get a very large tuning range as I uncompress and compress the coils like that, like a spring. I'm going to get a very high Q and very large tuning range as well. So I'll just have to fasten the coils down once I get them into place, I guess. Okay. Very cool, huh? Okay, so I guess it appears that I'm going to have to get everything in place, including my spark gap, when I design this, because all that inductance is going to have to be added in. That's going to add enough inductance that it's going to shift this. And oh, I just wanted to mention about Q. Q, you can measure Q with this network analyzer. That's another cool thing about this, is that it's all you have to do is measure the center frequency and then the half width, the two half frequencies on either side, and Q is the defined as the frequency divided by delta F, or the full width half max. And so you just need to take 3 frequency measurements. One, here, let me put this down. one at the center, and then actually you could probably just take a second one at the full width half max and double it. This thing's jumping around because the coils aren't fixed. So that would probably be about there. So that would be, and then measure the delta between there and there. And the Q gives you a measure of how much losses you have in your circuit, this resonant circuit, and tells you how true the frequency is going to be, and how long it will ring, how fast it will damp. Basically, you're going to have a damp decaying exponential oscillating function, and if it has a low Q, it's going to damp quickly. I'd like to have a circuit with a kind of high Q, although none of these components are super high Q. These are high voltage capacitors here. But so we can get the Q kind of high if we compress our coils a little bit. So let me fiddle with this, and hopefully we'll get a design going for some interesting circuits. Okay. Very cool, huh? Okay, so now I want to test the through option, or the through S-A-A-2 scattering parameter of this device using a couple different antennas. I just did a calibration from 500 megahertz up to the max 3 gigahertz. Looks like the calibration is mediocre at the higher frequencies. Again, like I said, this yellow trace should be much lower if the signal to noise was better, but it's only about 18 dB. And this green, this is the Smith chart. It should be exactly in the center. So since we calibrated and it's got, you know, the power going completely through the device, it should be perfectly matched, which means green point should be in the center, and instead of spiraling around the outside. So there's errors in the measurement there, but it's probably acceptable for what we're doing. Again, the blue trace is the through, these S-A-A-2, and so that is almost zero, which means most of the power is going through. Zero means almost zero losses. So that's a good calibration. And again, the purple one is the phase. It's just going through, you know, 0 to 360 and then starting over again, wrapping back around in the phase. Okay, let's hook up our antennas. We got a couple identical antennas, and we'll see if we can get coupling between one antenna and the other. And since I don't have long cables, I'm just going to do near field coupling of the antennas, just to see what kind of power gets through the antennas. That should be a good measure of that. Okay. Okay, so I have two antennas here. Let's take a look at these guys. Okay, they're kind of identical, pretty much identical. Log periodic antennas. Okay, let's take a look at that. Okay, there we go. Okay, so let's take a look at these antennas. They're pretty much identical, and right now I have one unplugged because I want to show the difference between when I have it. Let me put these so they're kind of facing each other. Now technically these antennas will radiate in this direction, but if they're close together like this, there'll be some near field coupling between them, between the side lobes. You know, this is only, that theory only applies for you know, far field. Okay, so I have my connectors unplugged, and we'll plug them in and see how it looks. First of all, let's just look at it with them unplugged. Phase is fairly flat. Of course, we shouldn't be getting any signal through, so this is just error. Remember, I told you these this network analyzer has, you know, this is what, 10, 20, 30, 40, 50 dB. It's getting noise, so this is like the noise floor, because there shouldn't be any signal coming in. Smith chart, since this is a transmit antenna, is going around the outside edge. That means it's total reflection, so that would be a bad VSWR if you use VSWR. So basically all the power is being reflected, is coming down the cable. It sees this open circuit, and it's being reflected back into the network analyzer, and that's what that means. And again, the S11, the reflected power is at 0 dB, which means that all the power is being reflected back. Okay, so let's plug this guy in. Okay. And when we plug him in, we should see these signals change a little bit. Okay, I gotta get that connector on there. Okay, there we go. So now we see the S11 came down a little bit, the yellow trace, so it's more matched over this region. There's actually power going through this cable and into the antenna here, right? We're getting power into the antenna now. And let's see if we can, come on. Okay, there we go. So purple trace, again, is the phase variation. We're getting a lot of phase variation up here. The Smith chart, over some of the range, it's not matched very well, so it's out toward the center of the circle, but then it becomes more matched over part of the range. And what we're really interested in is the blue trace, because the blue trace is showing us that we're receiving power here on the other antenna. So we're receiving power on this antenna over here. So there's waves traveling from here to there, and we're receiving that. And you can see that because the blue trace came up in power when we hooked up the cable. Here, let me unhook the cable for a second, and we'll see the difference. Okay, see, the blue trace went down, and we'll hook the cable back in, and the blue trace went back up. So we're definitely getting through power up here in the gigahertz range. So these antennas, as I suspected, were you know, based on the length of these dipoles. You can do the calculation, but those dipoles, I believe it should be quarter wavelength, right? Quarter wavelength dipoles. And there's a bunch of different ones, short ones at the front and longer ones at the back. That gives you a longer bandwidth, because the short ones will be resonant at shorter frequencies and the longer ones will be resonant at longer frequencies. So that will give you a larger bandwidth on your antenna. Okay, and the log periodics are supposed to be somewhat directional too. Okay, very cool. Let me, before we end this tutorial, let me go through some of the other options and see what else this nifty little device can do. I've been actually using it quite a bit more than I thought I would, because I've been using it to design my pulse power generator. It's good for finding resonant frequencies and other things. Very interesting, huh? Okay, so let's just go through a few of these options, other options, just so you can see what this thing can do. Like I said, the directions are absolutely horrible. I showed them earlier. Here's the main menu when you click on it, and let's see what we got here. We got, it says display, marker, stimulus, cal for calibration, recall, and I believe that's just recall cal, config, and pause sweep. So let's just do this bottom one first. Pause sweep will pause your sweep and prevent it from sweeping anymore. Okay. And okay, so we'll turn the sweep back on, so now it's sweeping again. Display, we'll go to the top. We have traces. You can change if you click on trace. Well, let's go back. We'll go through everything under display. It's trace, format, scale, channel, transform, flip display, and back. Let me do the flip display quickly. Okay, flip display is if you want the display to be upside down. Oops, I didn't hit it. You flip display. Now everything's upside down, so you can flip the device upside down and look at things from the other direction if you want to have it be upside down. Oops, let me get it back because this is confusing. So flip display back. Okay, so let's go to trace. So you can select one of the traces to change, although I've not really found a reason to change it because they show all the information you really need with the 4 traces that they have. But you can change the format of the traces. We have log magnitude, phase. I guess you can do delay, so you can do impulse response. I haven't tried that yet. Smith chart, SWR, and more. Let's just for the heck of it, let's just do delay. Okay. And I guess since we're kind of matched, I'm not really seeing anything. So the yellow one is now delay. Let's change it to SWR. Some people are interested in that. So there is our yellow one has been changed to SWR instead of it was log magnitude dB. Okay. So let's just change it back to log magnitude. And again, you can change any of the traces that you want using that same technique. Oh, there's even more. Oh, we can do polar, we can do linear, we can do real and imaginary. We can measure the resistance. Let's measure the resistance. Not sure what that scale means, but there. We're measuring resistance. Now, I guess it gives you an ohms value of what the resistance is. Oh, that's really cool. I wonder if it gives you the imaginary part too, or is that just real? Oh, wait, yeah. See, it says 11.9 ohms, and then it says 2.7 picofarads where the cursor is. So it gives you the real and imaginary parts of the reactance and the resistance of your load. Okay, where the cursor is, and I guess you can probably change using these buttons down here. You can change where the cursor is. Remember I showed you these buttons down here? So as I change that, see the resistance and the capacitance is changing, and I'm sure it will. See, it changed over to inductance now as it goes around the Smith chart. Now it's 21 ohms and 3.6 nanohenries. Okay, so that's a cool option. Let's do real. Of course, real and imaginary is going to look oscillating. And I typically use those on the network analyzer when I want to take the data out and work with it myself. Okay, so there's reactance. Of course, they're both displayed up here if you do. So it's just plotting the reactance. Reactance looks kind of like the phase, doesn't it? We're looking at the yellow trace again. Remember, I'm modifying the yellow trace right now. Okay, and linear, there's linear scale. Of course, log scale gives you more of a dynamic range than linear does. And let's do polar, what the heck. And of course, it's all over the place. Very cool, huh? Let's go back. Delay line. Okay, that would probably be better if you had a long transmission line. Cause remember, even the frequencies we're working with, well, I guess 3 gigahertz is, got a wavelength of, probably about this long or so. But probably about that long. Probably about between my fingers. You're not going to see very much of a delay in anything unless you have a longer cable. Let's just change that back to log magnitude. And we'll go back to the main screen here. Okay, so I believe that was a format that we're going through, right? So we'll go scale. And again, you can change the per division. It's at 10. I guess you can change the electrical delay, because you can set that where your reference point is in the delay to any point you want. Every time I change the scale division, let's just do that. You have to, okay, I guess it's on 3 dB per division. You have to enter something. You can't get back out of it once you get into this mode. And so it's kind of annoying. Let's go back. Okay, channel. Okay, so you can change whether there's 2 channels. One can do S, through out and reflected, and the other one can only do in for the through. So you can change the channel orientation, I guess, whether they call it channel 0 or channel 1 on this scope. Okay. And let's see, next option is transform, and I guess this is some kind of signal processing. You can do low pass or low pass impulse on transform. I'm not sure what that is. Okay, I guess you can turn the transform on. Let's turn that back off. Okay. Right now it's got band pass. Oh, you can do different types of windows. Normal. What is that? That must be a windowing function for the filters. Anyway, velocity factor. Again, you can't get out of this unless you enter something. I just entered a 1x. Let's go back. Okay, we already did flip display, and so I think that's all the options that we have there. So let's go back into the previous menu. So that was, what were we in? Display, marker. You can select marker. I guess you can do different operations on the marker. You can center. You can do a search. You can do a peak search, I believe. Search left, search right for maximum or minimum, or you can track an extremum, I guess. Let's see, operations, Smith value. Okay, guess you can change the Smith values so they're either in linear, log, real imaginary, or what's this, reactance, R plus L over C, which is the normal standard Smith chart. Okay. Okay, so we've done display, marker, stimulus. Again, I showed how to do the start and stop with calibration. Sometimes people like to choose the frequencies by center and span, which is a different way of doing it. You choose the center frequency and then you choose how far you span with the frequency range. You can change the number of points. Okay, right now it's 101. Oops, I changed it to 1 probably. Let's see, we'll change sweep points. 101. Oh, change it back to 101. There we go. Of course, I think we lost our cal when we did that, because usually when you change the start and stop value or the sweep points, you will change your calibration. It will lose the old one. CW frequency. Okay. Let's just do back. See, it won't let you do back unless you... Okay. There, I messed it up. Let me just reboot this guy, because I'm not sure how to set that back to where it's supposed to be. The good thing about this guy is when you reboot it, it just brings it back up to the way it was set before. Of course, it's uncalibrated, but oh well. Let's continue going through these different options. Okay, so what was that? Stimulus. We did stimulus, right? Sweep points. CW frequency, I'm not sure exactly what that is. But, oh, I know. You probably set it at a single frequency, and then it can just sit there and dwell and watch that frequency, because other network analyzers I've had can do that. So you can watch it in time, I guess. See how, just a particular frequency behaves in time, which is not what I wanted. Okay. Calibration. I've already showed how to do the calibration. Let's see, maybe we can correction. Reset. See, I don't see a way to reload the calibration. Oh, okay, maybe it's recall. Remember we saved it as 1. So there's our cal. We got our cal back after we reset it because we're able to save the cal. But I think that's all you can recall, right? You can't recall anything else, just the calibration. Okay, so the next one is configure. And I don't get this. I've tried. We have a touch calibration, a touch test. That's probably for the touch screen. We can save, I guess, the setup if you want to save the setup. I tried saving that. It doesn't give you any options other than it just saves just 1, I guess. Let's go back in the configuration. Here is the version of the scope. It tells you what software version this thing's running. And D message, God only knows what that is. Crystal frequency, 24 megahertz, touch cal. Okay, so it tells you the calibration of the touch. DFU, I have no idea what that is. You can enter DFU mode. I'll have to reset AND mode. I'll have to look into that. Pause sweep. I guess, is that it? Well, we could try. I was hoping that it would have some way to like save and recall, because it does have a micro USB port. You could save the actual data and recall it, but I'm not really seeing any option to do that. Okay. Device firmware mode. To exit, please reset the device yourself. Oh, okay. Well, okay, so that's to update the firmware. Definitely don't want to do that. Hopefully we didn't mess it up. Okay, there we go. And again, let me recall our cal, because we did save it. Okay. And I don't know. I don't see any other options. I can click everywhere on the screen, and I guess I can move the cursors around just by dragging them with my finger. That's cool. Look at that. I can click on the yellow cursor and drag it around. It's not okay. There, see, I dragged it to a different point now. Let me drag it all the way over here. Come on. I guess there's 2 cursors there. Now it's confused. Which one is which? I guess they kind of lock up. Okay, so let's grab a different cursor. Of course, again, you can move the cursors around with the buttons down here as well. Very cool, huh? Yeah, I still don't see a way to save anything, though. Okay. Okay, anyway. It's cheap and a very handy device so far. I've used it for a lot of things, and I think I'll keep on using it. You know, before I had it, I didn't know what kind of uses I'd have for it, but now I've been using it for designing my pulse power devices and checking out other things. It's a very neat and handy device. Has limitations. You know, at the higher frequencies, the signal to noise isn't great, but it's good enough for a lot of applications. Anyway, this is Dr. Janes, and thanks for watching. Okay, I just wanted to do one more test. I plugged this device into our computer here. I just wanted to see if it came up with any drives, because normally if you have some kind of device that can talk to your computer through USB, it will come up with a drive. It will recognize it as something it can read from. So Unfortunately, it looks like no drives came up, so I think that confirms my suspicion that there's no way to save the data from this guy. And of course, the directions are absolutely horrible. But anyway, it's a good device. I guess you can take pictures of the screen. You can write down the data points if you want to save a couple few. I don't even think there's a way to save the screen traces or anything. But it is a handy device. You can pause the screen, and here we have a picture of it now. Very cool, huh? I guess it's the only way you can save the data, take a picture of it. So, anyway, I guess that confirms our suspicions. But besides that, a very cool device. I like it. It's very cheap. Been useful so far. And got lots of projects I can do with this.